Class, in this video, we're going to look at integrating improper integrals. These are going to be in the form of a definite integral, but you may have an upper or a lower limit that approaches infinity or negative infinity, respectively. There may be one value that a graph is just not defined at, and we have to approach that from the left or the right. As always, I like to just jump right into an example and just show you the techniques, and between that and some experience, it usually doesn't take long to pick up on these. Let's look at the integral from 1 to infinity of 1 over x dx. Now, as a reminder, the 1 over x graph from 1 to infinity is going to be this area. And what we're doing is trying to decide whether this unbounded region has a finite area or not. Now, from 1 to infinity will be like this part of the graph underneath the curve and between that and the x-axis. For these improper integrals, if you have an infinity symbol, what we'll do is we're going to replace that with a letter. If it's an upper bound of, or upper limit of infinity, I like to use a B. If it's on the bottom of the integral, I'll use an A. It's just personal preference. I don't think it's a big deal either way. But once you make that adjustment, your problem will take this form. Limit as b approaches infinity, and then we'll write the integral with a 1 and a b. Limit as b approaches infinity. Okay, the antiderivative of 1 over x is the natural log of x. Since we're investigating only the positive side, we don't have to worry about absolute value. We do want to evaluate at 1 and b. Sometimes I use a little cursive b there too, by the way. Okay, so limit as b approaches infinity. Natural log of b minus natural log of 1. Do you remember what the natural log of 1 is? That's right, it's 0. For natural log, the larger the number that you take a natural log of, the larger your answer gets. So this limit is actually infinity, and this is considered a divergent improper integral. If you can get your limit to come out to a finite value, then it's a convergent, and that's actually the area. Sometimes there's a finite area to an unbounded region. Our next example, we're going to actually look at a case of that. Let's look at the integral from 0 to infinity of 1 over x squared plus 1 dx. This is one of our special types of antiderivatives, tangent inverse, or if you prefer to use arctangent, that's totally fine. Again, I'm going to replace the infinity with a b, but I've got to show that the limit of b is going to infinity. Just trade it out just like that. Okay, so that's our special antiderivative, arctangent, tan inverse, whichever way you prefer to write it. I'm going to write tan inverse just for brevity and to save a little bit of room. And we need to evaluate at 0 and b. The original problem, if you were to graph 1 over x squared plus 1, we're investigating this part from 0 to infinity. It's unbounded because there's an asymptotal on the x-axis, but it's possible that there's a finite area, believe it or not. Okay, applying the fundamental theorem of calculus, tan inverse of b minus tan inverse of 0 let's also recall what tan inverse looks like. It's probably been a while since we've done some trig. Tangent had vertical asymptotes at the odd pi over 2 multiples. Well, if you invert that, then you're going to get horizontal asymptotes at pi over 2 and negative pi over 2. And that's what tan inverse's graph looks like if you limit it to where it'll pass vertical line test. The farther out to the right you go on that inverse graph, you approach pi over 2. Right dead in the middle where 0 is, that's also 0. So tan inverse of 0 is 0, but tan inverse way out here at positive infinity approaches pi over 2. And so that's a case of where you have a convergent improper integral. And that's because we had a finite limit, whereas on the first example we had an infinite limit. It did not come out to a finite value. The next two examples are going to be very close in the way they look, but there's going to be a subtle difference with the integral length. Okay, so 1 over x squared, which happens to have a graph that looks a lot like 1 over x. From 1 to infinity, this is an unbounded region because of the asymptote. So I'm just going to pick a spot to be 1 to infinity. That's the rest of that area out there, and it's riding along the x-axis. Limit as b approaches infinity, integral from 1 to b. I'm going to rewrite that as x to the negative 2, because when we do the antiderivative property, it just makes it a little faster, a little easier to see. Add 1 to the exponent, divide by the result. That's going to give us negative 1 over x, evaluated at 1 and b. Limit as b goes to infinity of negative 1 over b minus negative 1 over 1. With a fraction, the faster that the denominator grows, the smaller the overall value of the fraction. For example, if you take a cake, the more pieces you cut it into, the smaller each piece becomes. If this is approaching infinity, then that is going to approach 0. These two negatives are going to make a positive 1. So this has an overall limit of 1. that's a finite value, so we have a convergent improper integral. Now that's weird. By adding a power of 2 or having a power of 2 in the denominator, it suddenly converges, where on the very first example, it does not converge, it's divergent. Turns out, if you have an integral in this format, or like the one on the first page, actually at the end of your homework online, there's a problem that asks you to determine the value of p that determines convergence or divergence. And as long as that power is greater than 1, like on this example, we had an original power of 2, it converged. If that's a 1 over x cubed, it's going to converge. Anything less than 1, like 1 over square root of x, 1 over cube root of x, if your integral is going from 1 to infinity, they're going to be divergent. Okay. The last example is going to look a lot like this one, except we're going to change our integral limits up. And we're only going to integrate from 0 to 1, whereas in the last 3 examples, we've always gone from a finite number to infinity. One over x's graph from 0 to 1 is still that quadrant 1 portion. It's still going to look like that. But to go from 0 to 1, we're looking at this asymptotic part until we reach 1. And so there's where we're looking at for area. It's unbounded because there's an asymptote along the y-axis. And it just depends on if our limit comes out to a finite or infinite value as to whether that's a definite, specific, I guess is the best word for it, area. Sometimes they just don't get towards their asymptote fast enough to have a finite area. And that's really what it boils down to, is if it can get to the asymptote fast enough, it will have a finite area. Now this time, the asymptote is the y-axis, where x approaches 0 from the right. Little bit different setup. You pick a letter. I usually use A for a bottom limit, B for an upper. And you can tell from the previous 3 examples, the B has always gone to the top, but that's because we started out with a positive infinity. I'm going to still write that as x to the negative 2, just to expedite the antiderivative. Okay, our shaded area is approaching 0 from the right side. Our antiderivative will still be the same, negative 1 over x. We're going to evaluate at a and 1. And then once we put those in, we're going to let a approach 0 from the right. Negative 1 over a minus negative 1 over... I got to reverse that. Top value, negative 1 over 1 minus negative 1 over the bottom value, which is a. It's always top minus bottom. I just got a little carried away. Negative 1 plus 1 over a Now with a fixed numerator, like in the last example, the larger the denominator becomes, the smaller the fraction becomes. It was that cake analogy of the more slices, the smaller each slice is. This time we're letting the denominator get smaller and smaller. What does that do for our fraction? It makes it get larger and larger. You got it. -1 plus infinity is infinity. So this is a divergent improper integral.